Our discussion on classic vectors is split into three parts. We have already discussed plasmids and phagemids. This video focuses on bacteriophage and cosmid vectors. I will take the example of Lambda Phage vectors to illustrate this concept. This is different from the use of M13 phage we saw in phagemids. Lambda Bacteriophage vectors quite literally use the viral DNA as a vector. They have double-stranded linear DNA that is strictly around 50 kb in length. The weird bit about their genome is that the edges of the DNA have a single strand overhang, which is exactly 12 nucleotides in length. These ends are cohesive, or sticky, and for that reason we call them cos site ends. More specifically, the cohesiveness means that the ends of the viral DNA can come together to form a circular DNA. The circularization of cos ends generates a 12-nucleotide, double-stranded cos site. This cos site is part of a bigger 200 base long cos region. I will discuss the full cos region when we get to Cosmids later in this video. The Lambda Phage vectors depend on a few things. First, you can only insert about 5% extra DNA in the original Lambda DNA. 5% of 50 kb is around 2.5 kb, so that is the upper limit. Typically, this translates to finding a neutral region and inserting your DNA in that region. This type of usage of Lambda DNA makes it an insertional vector. Second, you can remove about 25% of Lambda DNA without affecting the life cycle of the Lambda virus. Let's say that 25% corresponds to this region here. This means that you can replace this segment of DNA with your specific DNA. This type of usage of Lambda DNA makes it a replacement vector. Side note, the nice thing about viruses as vectors is that you don't have to make special bacteria called competent bacteria to insert your DNA. Lambda phages naturally infect their host, so the entire process bypasses the need for any special bacteria. We will discuss competent bacteria when we get to delivery methods. Anyways, let's expand on the insertional vector. Insertional vectors typically use a single restriction site which can split the viral DNA into two parts. And you take your piece of DNA that is compatible with the restriction site. This piece of DNA has a limit of 2.5 kb. This insert can go into the split viral DNA, resulting in the final vector. Since the ends of the vectors are cohesive, it can circularize. When it is inside the bacteria, this vector can be used to make virus particles, since nothing related to the virus life cycle is removed. And it can be packaged into new virus, and you can continue propagating this insertional vector through viral infections. Insertional vectors were first iteration of classic vectors, but they became useless when replacement vectors were developed. Replacement vector rely on cutting the lambda DNA at two locations. This region, the middle fragment, typically contains two viral genes called red and gam. This fragment represents 25% of junk stuff that can be removed without any problems. Once you have removed this internal fragment, your choice of DNA can be used to replace this junk stuff. 25% of 50 kb means that you can remove up to 12.5 kb of the viral DNA. Given that we can add another 5% to this entire mass, your DNA insert can be around 12.5 kb to 15 kb. The fragment that you remove and replace is called stuffer fragment, literally junk stuff. The end story of replacement vector is similar in that the ends can be connected together to form a full circle, which can be propagated into a bacteria through a viral infection. A big difference in the use of lambda DNA as a literal vector is the lack of any selection or screening markers. We have either replaced some portion of the viral DNA or inserted some DNA. Insertionals are useless to begin with, but replacement vectors remove this junk stuff that contains red and gam genes. These two genes play a role in giving rise to the SPE phenotype, which can be used to select if your fragment got inserted. For this, you have to understand the concept of P2 lambda interference. P2 and lambda are both bacteriophages. The interference starts when the P2 phage infects the bacteria for the first time. And in its life cycle, the viral DNA gets stably integrated into the bacterial genome. In this scenario, the bacteria is doing fine because the viral DNA in its genome isn't actively making new virus particles. Technically speaking, this bacteria is lysogenic for P2. And the phase in which the process of viral DNA integration occurs is called lysogeny. Following this, you can have a Lambda phage try to infect this bacteria. But surprisingly, the Lambda phage will be unable to grow. Since the genome of P2 phage is already part of the bacteria, the Lambda virus is somehow sensitive to the P2-driven inhibition. This is the Sp plus version of the Sp phenotype. Being a lysogen for P2 stops Lambda infection. This inability to grow or sensitivity to P2 comes from the presence of red and gam genes. If you were to remove the red and gam genes, then the Lambda phage will be able to infect the P2 lysogen. If it can, it is no longer sensitive, and we call it the Sp negative phenotype. Now, if we circle back to the replacement vector, all events that failed to remove the stuff, or somehow the stuff got reinserted after the split, will contain the red and gam genes. This will result in a failed infection, meaning no viral growth and no visual viral plaques. In the other case, if you replace the red and gam genes, the viral growth is visible through plaque formation. This is how the Sp phenotype, which works similar to selectable markers, can be used to positively select for your bacteria of interest. Now on to Cosmids. Cosmids are vectors where the Lambda cos site is inserted into a plasmid. This is in contrast to Phagemid, where the origin of M13 phage was inserted into a plasmid. So once again, a very different vector. Understanding Cosmids is a bit tricky, but if you understand the 200 base cos site, it becomes easy. The cos ends of the Lambda DNA can circularize to result in a fully functional cos site. The cos site has three main subregions: cos Q at one end, cos N in the middle, and the larger cos B, which is a bunch of repeating units. These repeat units have names like R1, 2, 3, and I1, 2, and 3. You may recall them from the origin of replication in E. coli. Cos-Q primarily functions to terminate the viral DNA packaging. Yes, you need all these three sites, with some proteins to terminate the packaging, but Q plays the leading role. The repeat regions of Cos-Q play a major role in DNA bending and assists in DNA packaging. This bending of R and I repeats is identical to what we saw in ORI-C DNA melting for initiation of replication in prokaryotes. The I1 works very similar to the bacterial IHF site. The viral DNA, among many other proteins, encodes for a particular protein called protein A. If you have watched my Phi-X174 rolling circle amplification video, you know it is a terminase, meaning that it will find a specific site and nick it. So protein A cleaves the cos-N site, generating a 12 nucleotide overhang. Effectively, the cos-B and cos-Q are separated by the N site. These left and right ends are often called cos-NL and cos-NR. This linear piece of viral DNA with 12 nucleotide overhangs is what we have been referring to as the linear genome all this time. Cosmids are just fancy plasmids with a size of around 5 kb. The inconvenience of using Cosmid is that the DNA you are trying to insert must be in a range of 35 to 45 kb. This comes from the fact that Lambda DNA is 50 kb. The Cosmid DNA will be used for packaging into a Lambda virus, so the total size of the Cosmid needs to match the Lambda virus DNA size. Lambda virus proteins have a strict range of DNA length that is allowed to be packaged. The original intended use of this range was to clone big genomic fragments for gene mapping, subcloning, or shotgun sequencing. Here is one of the first Cosmid vectors. This 5.4 kb vector is based on the POC19 plasmid, since it carries the COL-E1 origin of replication. It has ampicillin for antibiotic selection. More importantly, it has full-length cos region. Things to focus in on this plasmid are specific restriction sites, and I will choose BAMH1, HIN3, and SAL1, and how they're oriented with respect to the cos region. So you take the Cosmid vector and open this vector in two different ways. One using BAMH1 and HIN3. HIN3 is next to Q and B sites, and the ampicillin facing the B site. With this, you have removed the tiny portion between BAMH1 and HIN3. The other way to cut this vector is using SAL1 and BAMH1. In this, you want to keep the DNA fragment with the Cos site. If you write the structure of this, you will notice that it does not contain the ampicillin resistance. Once you have these two types of parts, you can take the genome of interest and make a genomic library by chopping up the genome into tiny bits. My enzyme of choice is SAO3A1, and in a moment you will see why. This chopping is done in such a way that you maximize the fragments of length 35 to 45 kb. These fragments generated by SAO3A1 are compatible with BAMH1. The sticky ends generated by both these enzymes are GATC. So looking at the ends alone, it is as if BAMH1 had cut it. If you watched my restriction enzyme video, you know we call them isocautomers. These BAMH1 compatible fragments generated by SAO3A1 can be inserted in between these two parts of the vector. If you do that, you create a large fragment. All this is happening in vitro, meaning outside the cell in a tube. While this occurs, you also grow two fractions of bacteria on the side. One fraction expresses half of the lambda virus proteins, and the other fraction expresses the remainder. Since none of the fraction has a complete set of proteins, the virus cannot form. But you can take all these virus assembly proteins from the soup of these fractions and combine all of them together with the DNA in one single tube, or in vitro. The A protein, as we discussed previously, is the terminase protein, which can nick the Cos-N site. When it cleaves Cos-N, you release the Cos-NL and Cos-NR regions at the end, and you will have the major internal portion of the fragment containing your desired piece of DNA. If you notice, this looks exactly like the depiction we had before, except that the orientation is reversed, which doesn't matter. Once you have all these components mixed and the fragment is nicked to generate single-strand overhangs, the virus particle can form, which will contain the Cosmid DNA. Again, to be very specific, this is called in vitro packaging. The virus assembly and packaging happens in a tube, not inside a bacteria. This is fine, but let's go one step further and think about these free Hin3 and Sal1 ends, and the fact that this same or similar fragment is present in millions of copies. This means that all such fragments with free ends can form concatemers. So if you take this fragment, it is very likely that a free Sal1 can stick to another copy of itself, forming a tandem repeat. This same thing can happen with Hin3 ends as well, resulting in a much longer repeated fragment. Many possibilities, but regardless of the repetition, this fragment ends up with many Cos sites, and we care about the Cos-N for simplicity. What if the protein A nicks these two Cos sites? Do you think the resulting DNA will be packaged into a virus? If you think about this specific segment, you will notice that it is quite literally the end-to-end version of a starting Cosmid vector. This vector is around 5 kb. This is too short for packaging because the DNA should be close to 50 kb to be compatible for packaging. The other option is this extreme N situation. In this, you have two large 35 kb long fragments plus a bunch of Cosmid vector DNA. This is clearly longer than 50 kb and it will not fit. The other option is this N to this N. It has the 50 kb part and another 5 kb part. This will also be slightly too long for packaging. The optimal DNA length for packaging most likely occurs when these two ends are nicked. That is the simple scenario I illustrated here to get this piece of Cosmid DNA. So even if all ends are nicked, you will only have the optimal length of Cosmid DNA packaged into a virus head. Once you obtain your in vitro assembled virus particle, you can use them to infect your choice of bacteria. This will inject the linear Cosmid DNA into the bacteria. The Cos ends will find each other and circularize, resulting in a circular Cosmid DNA. So in simple terms, this is a large 50 kb plasmid with Cos sites, and it has your inserted DNA. It does not carry any genes to make any of the viral proteins, meaning it cannot form a lambda virus. This Cosmid DNA propagates as a normal plasmid, with a copy number of around 15 to 100 copies, depending on the vector optimization. If you're interested, there is something called as Phosmid, which on top of Cos sites contains lambda DNA origin of replication. This is essentially a variant of combining phagemid properties with a Cosmid vector. Again, if you're interested, Google is your friend. I hope this discussion was somewhat useful. And as always, I will see you in the next video.